Imagine a coin flip. Heads or tails, a 50-50 chance. But what happens if you flip it 1,000 times, or 1,000,000? Does the randomness truly balance out? This brings us to the law of large numbers, a cornerstone of probability theory. It states that as you increase the number of trials in a random experiment, the average of the results obtained will get closer and closer to the expected value. Think of it as the universe's way of ensuring long-term stability amidst short-term chaos. This principle is why insurance companies can accurately predict claims, even though individual accidents are unpredictable. Now, let's shift our focus to sequences of events, where the future depends only on the present state, not on the entire past. This is the essence of a Markov chain. It's a mathematical model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. Consider a simple weather model. Today's weather depends only on yesterday's. If it was sunny yesterday, there's a certain probability it will be sunny today, or rainy. The day before yesterday's weather doesn't influence today's, only yesterday's does. This memoryless property is what defines a Markov chain. This concept isn't just theoretical. It found fascinating applications, even in games. Stanislaw Ulam, a brilliant mathematician, explored the behavior of solitaire using these ideas. He realized that the sequence of moves and card distributions could be modeled as a series of states, leading to insights into the game's solvability and probabilities. Ulam's work, alongside John von Neumann, also played a crucial role in understanding complex physical phenomena, like nuclear fission. Simulating the behavior of neutrons in a reactor was incredibly difficult to do analytically. They needed a way to model the probabilistic paths of particles. This challenge led to the development of the Monte Carlo method, a revolutionary computational technique. It uses repeated random sampling to obtain numerical results. Instead of solving complex equations directly, you simulate the process many times, and the average of these simulations provides an approximation of the desired outcome. It's like throwing darts at a target to estimate its area. The Monte Carlo method was instrumental in the Manhattan Project for simulating neutron diffusion, but its applications extend far beyond physics. It's used in finance for risk assessment, in engineering for reliability analysis, and in computer graphics for rendering realistic images. It's a testament to the power of randomness in solving deterministic problems. From the realm of physics and games, let's jump to the digital world. Before Google, the internet was a wild west. Early search engines like Archie, Veronica, and Jughead were essentially glorified file directories. They indexed file names and titles, not content. Lycos and AltaVista later emerged, attempting to index full text, but their results were often noisy and irrelevant. Then came Google, born from a research project by Larry Page and Sergey Brin. Their breakthrough was PageRank, an algorithm that didn't just look at keywords, but also at the link structure of the web. A page was considered important if many other important pages linked to it. This revolutionary approach transformed how we find information online, making search results far more relevant and useful. Speaking of relevance, how does your phone know what word you're about to type? This is predictive text, and it often relies on Markov chains. When you type "how are," the system predicts "you," because "RU" is a highly probable sequence in its language model. The probability of the next word depends on the current word or a short sequence of preceding words. This brings us back to the memoryless property of Markov chains. In the context of predictive text, it means the system primarily considers the immediate preceding words to predict the next one, rather than trying to recall the entire sentence history. While more advanced models use deeper context, the fundamental idea often starts with Markovian principles. Finally, let's apply these ideas to something tangible. Shuffling a deck of cards. How many shuffles does it take to truly randomize a deck? This seemingly simple question has a complex answer rooted in Markov chains. Each shuffle can be seen as a transition between states of the deck's order. Research, notably by Percy Diakonis, has shown that for a standard 52-card deck, 7 riffle shuffles are generally sufficient to achieve a state of near-perfect randomness. Fewer than 7, and the deck retains too much memory of its previous order. More than 7, and you're just doing extra work without significant improvement. It's a beautiful illustration of how mathematical principles govern even the most common activities.